this formula is known as Rodriguez rotation formula. This is the foundation for all the attitude representations that we're going to look at. So this actually describes one of the attitude representation, which is known as axis angle. So let us just see what is inherent in this. So in this representation, then we have one vector n, then we look at any other vector v. And then we look at what happens if we rotate it alpha radians around n. This is what this formula describes. Any attitude can then be represented by such an angle and such a vector n, and then how this then generates a coordinate system in which all of the vectors v marked can be decomposed. So what I want to do now is to sort of derive this formula, though what I'm going to do is rather to verify that it works in a very special case, which again can be used as an argument for general validity. So the case I want to look at is when this vector n is simply equal to the z-axis unit vector. So that's perhaps the simplest possible case I can consider. So let us then see how this works out in that particular case. I have this vector v marked. It's then going to be 1 minus cosine alpha. And then I'm going to have this n vector first as part of an inner product. Just write out the details for my v vector 2. Then I have the second term here. And then I have the sine term. First the n vector, and then the cross product of that. And my v vector. So here I'm just going to delve into the nitty-gritty algebra. So for the first term, I'm going to end up only have the upper two. This becomes a scalar times the cosine times this vector. So in the first two slots, I am going to just have zeros. And then for the last element, I'm going to have this cosine times 1 times vz. So then I'm looking at this cosine term, which is very straightforward. Just take cosine alpha times all the elements. finally, then I have the cross product over here. There I'm now going to take the cross product of the unit z vector with arbitrary vector, and what then happens is that I get out these two elements while this one vanishes, because it's tangential to the first vector in the cross product. So for the first one I get the dy, get the minus, and then the next slot I'm going to get Vx, and then since it was minus at here, that's going to be positive. And a 0. And then I need to try to organize this a little bit. Now it's a bit messy, but I can stitch these things together so I get a single vector. So for the first two, I have these cosines and these sines. This should have been y over there. And for the last element, I have vz, cosine and 1 minus cosine, so I end up with just vz. So how can I write this? I want to make it a bit clear what's going on by introducing the concept of rotation matrices here. So when I look at the first thing here, I sort of see that this is the same as what you get out of a rotation matrix in 2 dimensions, because I can write this as this. Right, and then if you take this matrix times this vector, then this is what you're going to end up with. So what remains then is just to introduce a bit more notation, just for the sake of it. So let me call this matrix R alpha. This is my general notation for 2-dimensional rotation matrix. When I write capital R and some argument, some scalar, then that's a 2-dimensional rotation matrix times this vector. And this again, what is this? Well, I can say that this whole thing is the rotation around the unit z vector with angle alpha times v. So then we have seen that this rotation formula, in the case that n is the unit z vector, what I end up with is just rotating stuff around the unit z vector, meaning that vz is not affected. Once this is established, then you can make an argument, which I'm not going to do here, but you can make an argument that you can transform all your vectors into any other coordinate system, and then this formula will still hold. So then you have a general rotation formula and a general representation of amplitude in terms of angle and axis.